all the videos regarding this particular structural geology class. Okay, so I welcome you again to the structural geology course this year. So before we get into the actual business, of course, these are the books that I want you to follow. Hopefully you can see my screen. Just put it in the presentation mode. So the main book that I am going to follow, like we followed Laudu's book in case of geophysics. The main book that we are going to follow is S.K. Ghosh's book on structural geology. This book is available in the library as well as online. You can find it out. And these are the reference books like H. Fawson's Structural Geology. He has a nice, beautiful website as well. Most of the content of the book is, if you write, Hakon Fawson in Google, you will be finding his website. It's a pretty nice website. You can find material there. This is a very classic book by Ramsey. This book is also available in the library. There is another book of Twist and Moore. This is also available in library. But these three books you will use as reference for more advanced reading. But this book we will follow like our everyday reading. Okay. There are other online materials as well which I have listed here. Of course, I need to thank the NPTEL of IIT Kanpur, Professor Shantanu Mishra, Professor Hakon Fawson, book of S.K. Ghosh, from where I have taken the slides and used them for this particular course, part of it. And now let's talk about your assessment. It is going to be exactly like last semester. So like 20% will be for your end sem exam. Okay. And then around 10% for your attendance. Attendance means whatever assignments and quizzes we will have, that you will have to fill it up and submit. And then of course the rest of it, so then 70% will be all the interim evaluations, be it assignment, be it quiz. Okay. So yeah, please make sure that you submit all of them like you did, most of you at least, for solid earth geophysics. Okay. So that's how we will evaluate the course. Now let me just switch off. Okay, so what is actually structural geology? I hope you have got some idea of what structural geology is all about. But let us try to see with more definitive terms. So structural geology is commonly used together with tectonics and geodynamics. So they are very much synonymous. If I break structure in Latin means build. Tectos, from where the tectonics term comes, means builder. And dunamis, that is a Greek word again, that is the basis for geodynamics, means power or force. So the subject concerns in general the shape, geometry, displacements, kinematics, and forces, mechanics in the Earth and planetary bodies. Okay. So we are going to look at structural geology from three approaches, of course. One from the shape approach, from the geometrical approach, one from the kinematic approach, and one from the dynamic or mechanical approach, where we will talk about forces. Okay? And it's a highly interdisciplinary subject. Of course, it has a lot of components from material science, mechanics, physics. Perhaps we will have some, if you want to do some advanced stuff, computer science, remote sensing, geophysics, petrology, of course, geodesy, and survey. So all these things come together while we study structural geology. So as you see that I have talked about three different terms: geometry, kinematics, and dynamics. Okay. So all these three things will be three different approaches, that will construct our understanding on structural geology. Now, by geometry, we mean, of course, 3D geometry. Okay? So it's very important that we are able to see things in 3D. We are able to understand and visualize things in 3D. That is a fundamental aspect of structural geology. You have to be able to, if I say a fold, if I say a fault, the picture should be pretty much evident in your mind. Okay. And it's not going to be as simple just stating fold or fault. There will be further complicated structures, and the structures should be very much evident in your the 3D shape of that body should be very much evident in your mind. Kinematics. Kinematics means with the study of displacement of strain. Okay, study of displacement. We will see what it is in general. Say, for example, we are going to see perhaps there is a point, and with after applying some force, there is a sort of movement in that point. With some sort of vector u. We call it displacement. You can call it strain. So kinematics means after you apply some sort of force on a particular body, the type of changes, the process through which the change actually happens. We call it as kinematics. So that is something we are going to look at as well. And of course, we are going to look at the dynamics. Dynamics means the forces responsible to forces responsible for the kinematics. Okay, forces. Okay. And here we are going to also study a lot of mechanics, right? A lot of mechanics. Okay. So if I just try to summarize what we have discussed, I have like a simple material, okay, where I apply some sort of force, okay, and this goes through a kinematic process to, develop a final structure which has a definite geometry. So we are going to study about these forces. We are going to study about how these forces essentially makes those changes. That is my kinematics. And of course, we are going to study the final geometry. Okay, is that clear? I hope it is. Okay, now let's start with some very basic geometries. Okay, and I hope these are a little bit of a recapitulation for you, but nevertheless, let us everyone be on the same page. Some very basic geometries, very basic 3D geometries. By the way, your lab class will be primarily around understanding these basic 3D geometries through complicated maps and stereographic projections. Okay, right. So in the nature, wherever we see any rock bodies, or any exposure, yeah, there are few things we need to observe geometrically. Okay. The first thing we need to observe is a line, and the second thing we need to observe is a plane, right? Now, what is a line? Line is nothing but, uh, I can divide line into a number of infinite number of points, of course, and then when an infinite number of point lines actually join together can form a plane. Okay. So we are going to look at how we are going to geometrically define the attitude of a line and the attitude of a plane. Okay. So we have to have some sort of parameters that can be very distinguishable from one line to the other. And there should be some sort of parameters which are also distinguishable from one plane to the other. Okay. So to do that, let us start with a line, a very basic one. And for the time being, we are only considering straight lines. Okay. So because curved lines are nothing but, you can actually subdivide them into a number of straight lines as well. Okay. So line. In geology, line has a very, technical name. We call it as lineament. Okay. So it's the same thing, but technically we call it as a lineament. Okay. Now a line which is, hanging in space. Okay. We have to define certain parameters around this line. So what I'm trying to do, so this is like, simply hanging in space. So let us define certain coordinate system around it. So let us define some horizontal coordinate system. Okay. Suppose this is X, this is Y, and then of course there is the Z direction. Okay. So the XY plane is the horizontal plane. Okay. Okay. And then suppose XZ and YZ, these two planes are vertical planes. Okay. So this is the line, suppose OA. Okay. So there is these three coordinate, this beautiful Cartesian coordinate system where I have this particular line OA. Okay. So what I'm first doing, I am essentially, projecting this line OA on the horizontal plane. Okay. Let's use a different color. So I'm projecting this line OA on the horizontal plane. So this is OA dashed. So OA dashed is the horizontal projection of line OA. Okay. So now suppose I had to actually, so this is the angle, okay, between the line OA and its horizontal projection, OA dashed. Let us say this angle is theta. Okay. And this theta angle, we call it as plunge. Okay. So the angle between the line and its horizontal projection, yeah, is called. Okay. As simple as that. Now we are in the geographical reference system, so we can be a little bit smart, and rather than putting XY as our coordinate system, what I'm trying to do, I will just put rather than XY, let's put in case of Y, let's put here north, then this will be east, right? Because it's like 90 degree, and then I'm going clockwise, right? So north and east. I can simply replace x and y from with north and east, right? Now, the angle of this line O dash, OA dashed with north, yeah. So this is phi, this line phi. Okay. So you can see that angle phi is on the horizontal plane, okay? But angle theta is in the vertical plane, right? Angle phi is in the horizontal plane, and angle theta is in the vertical plane, right? So angle theta is called plunge, and angle phi is called trend. Okay. So the angle between the horizontal projection of the line with respect to north is called its trend, and the angle between the line itself and its horizontal projection is called. Do you have any doubt around it? Anything you did not understand? Anyone? Any doubt?
Excuse me, sir.
Yeah.
Sir, plunge angle and the dip angle are same.
No, I just hold that thought. Deep is used for plane. Deep is not used for line.
Okay, sir.
We are right now only discussing about the line, right? So it's the line is defined with trend and plunge. Okay. So plunge, is that clear, everyone? What is plunge? What is trend? And that is exclusively related to a line.
Sir,
Everyone? Yeah.
sir, is it the same trend, same definitions which was mentioned in the lab course in second
Yeah,
year?
yeah, yeah. Absolutely same. Yeah.
Okay.
Absolutely same. But is it clear, everyone? What is plunge? What is trend?
Yes, sir.
Yes, sir.
There should not be any doubt. Okay. I hope everyone is clear with what is plunge, what is trend. Okay. So that's how we define a line. Okay. Now let's see. Now let's look at a plane. Okay. So to do that, let's have the coordinate system defined. Again, I'm choosing north, east, and vertical z. And then suppose I have a plane which looks something like this. Yeah, which is an inclined plane. So this is my inclined plane. I hope you can understand, you can figure out the 3D geometry. Okay, so this is my plane. Okay. Let's say for making it a bit more general, let us say this is my plane. Let's say this is not north. The north axis is here. Okay. It's just a bit more general. Okay. This is my plane, and the north is here. Okay, so this angle, this angle is 90. Yeah, okay, that plane is horizontal, and here is my here is an inclined plane which is demarcated by this green color. Okay, this is the plane with respect to which we are going to define its attitude. Okay. Now, so a plane, like a line was, we have defined a line. A plane is defined with respect to its strike and dip. Okay. So now we said this northeast, this particular plane, is the horizontal plane, right? This is my horizontal plane. Right? So this line OA, this line OA is nothing but the intersection between the plane of our interest, which is OA, say BC, and the horizontal plane. Right? So this line OA is nothing but the intersection between the plane OABC and the horizontal plane. Okay. And so this OA is actually a line, right? Because it is the intersection between two planes. So the angle of line OA, so the angle between north and OA will be called its the angle between the north and the horizontal projection, and the intersection between the plane and the horizontal plane. That angle, this is what we call as, let's say, suppose we call it theta. Theta is strike. Okay. And the angle between the plane and the horizontal, that we'll call it. Let's say this is more conventional. So phi is the strike, and the angle between the plane and the horizontal, that is theta, and that is what we call dip. Okay. So let me just do something. Let me just switch on the video for a moment and show you what it is. Let me. Okay. I hope you can see the demonstration, everyone. So suppose this is my horizontal plane. Okay. And here is a inclined plane. Yeah, here is an inclined plane. So the angle between the horizontal plane and the inclined plane, the angle between the horizontal plane and the inclined plane is called dip. Okay. And then what I can do, I can actually, you see, I can draw a line here. This is a line with the pencil I have drawn. That is nothing but the intersection of this particular blue plane with the black plane. The black plane is the horizontal. There is a line. This is the line of intersection. And I can actually now, this is a line. And then, of course, perhaps here is my north. Okay. So suppose so this is the horizontal plane again. Okay? So I got the intersection line here, and then suppose this is the direction of the north. So this is phi. That will be my strike. Okay? That is measured on the horizontal plane. So I have to simply understand the intersection of the horizontal plane with the plane that I am interested in and the intersection that we have, right? Uh, the angle between the north and that intersection line is the strike, and the angle between the plane and the horizontal plane is the dip. Okay? Is that clear, everyone? You can ask me now. Anyone having any doubt? Because these are two very basic and fundamental definitions. There should not be any doubt around it. I'm happy to explain more than once if you have a doubt. Try to visualize it as well in your mind. I hope it is clear. Now, let's go to some more understanding. So let's.
So in the previous diagram that you've drawn, there you
Yeah.
have said that theta is the dip, if I'm not wrong.
Yeah, theta is the dip. If you are considering a plane, yes.
So,
Is
but
the angle between the, I mean, it doesn't matter whether you call it theta or phi, it's the angle between the horizontal plane and the plane itself.
so but
Is
in the
the
previous diagram, the theta angle was actually horizontal, not vertical.
where?
The one that you had drawn before this.
Oh, sorry. This will be phi actually. That's why I should have been.
Yes. Okay.
My apologies. Because convention is you use theta for dip. Okay. One is not going away. This is phi. Okay. This is not theta. Theta is this angle. Okay. Right. Now, let's say I'm drawing a special situation. So suppose this is north, this is east, this is vertical, and here is my plane. Okay. So what is the strike of this plane? Tell me. What is the strike of this plane? What is phi? What is the strike of this plane?
Zero.
Sir,
Zero
degree.
degree. Absolutely. Simply because it doesn't have uh, any angle between the north and that horizon projection. Right? So this angle is zero. So the strike is 0 degree. Okay. Now, what I can do, so this is my strike line, right? Which is in this particular case parallel to north. Okay. What I can do, I can also draw a line in the horizontal plane itself, which is perpendicular to the strike, right? So suppose, so this angle, okay? So this is OA, this say BC, the direction BC, okay? So what is the, so that what is the angle between north and BC? So angle in BC is then 90 degree, right? Okay. So the direction of BC, this direction is called dip direction. this direction is called dip direction. So dip direction is always strike plus 90°, okay, or strike minus 90°. What do I mean by strike minus 90°? So let's see another situation. Z. Previously, I had drawn a plane which was like this. Now I can also draw a plane which is, you know, they have the same dip. They have the same dip, but they're opposite. They're the dip direction. So dip direction is exactly opposite to each other, right? So the dip direction in this particular case, I will get, so so this is BC, this is BD. In case of BC, I get it by adding 90° with my strike. And in case of BD, I get it subtracting 90° from my strike, right? Because it is in the opposite direction. Okay? But they can have exactly similar dip. So they are like the conjugate plane. Okay? So these two planes will be called as conjugate planes. Conjugate plane means they have exactly the same dip, but they have opposite dip directions. So now if I have to define a particular plane, okay, I have to define a particular plane, there are three things that I will be needing. Three things I will need. So if I define a plane, I will need three things. First one is its strike, then I will require its dip, and then I will require its dip. Okay. So for the examples that just I have discussed, here the strike was 0°. Suppose the dip was 30°, and the dip direction could be towards 90°. That means towards east, or it can be 0°, 30° towards 270°. Because that is so 0. So now if I look at this circle, which is my horizontal plane, this is 0, this is 90, this is 180, this is 270. So this is north, east, south, and west. Okay. So 0° plus 90 means towards 90°. The dip, the plane that dips towards 90°, 30° dips 30° towards 90°, or 0° dips 30° towards 70°. Okay, that is exactly opposite to 90°. Okay. So now, how do I get my dip direction? I have to either add 90° to my strike, or I have to subtract 90° from my strike. Okay, then I will get my dip direction. It is either of these two. And dip is a different quantity. Dip is, of course, the angle between the horizontal plane and that particular plane. Now, you can you see what I had drawn previously, that this is north, east, this is Z, and this is how I had drawn my plane, right? So this is the the strike is 0 degree, I can also say the strike is 180 degree. It doesn't really matter. Okay, because so this is the line of intersection, right, between the horizontal plane and that particular plane. This is the line of intersection. Okay. So I can write 0 degree or 180 degree, doesn't matter. So I can simply replace that with 180. Okay, it will still refer to the same plane. Okay, so adding 180 to the strike doesn't make any change. Okay? You can always add or subtract 180 from your strike. It will still imply to the same plane. Okay, but you cannot do that with respect to your deep direction. So the deep direction has to be 90 degree. It refers to a particular direction. So if I add, so you can see the difference between these two is also 180. But if I add or subtract 180 degree, this defines two different planes, okay, which are conjugate to each other. Okay. Now, so I can have any plane, 120 degree strike, 45 degree dip towards. So what would be the dip direction? Can someone tell me what would be the dip direction? If the strike is 120 degree, dip is 45 degree, what is the dip direction?
Sir, 30 degree or
Yes,
210 degree
30 degree, another will
or
be 45 degree, 210
210.
degree, right? Okay, but now I can also replace 120 with what? What I can write instead of 120?
Sir, 300 degree.
300. Absolutely. So 300 and 120 degree is no problem. They are same thing. Okay. You see, the difference between these two is also 180 degree. Yeah. But you cannot interchange them. Yeah. Now you have to understand this whole concept with understanding the 3D geometry. Okay. So what we are exactly meaning? What does 300 degree means? 300 degree means that the intersection between that plane and the horizontal plane is a line which is along 300 degree. Okay, which is along 300 degree. 300 means somewhere here, right? 70, 30, 300 degree here. You see 300 also means, so this is the line, right? So 300 also means what? 120, right? They're the same thing, right? So that would dip either towards 30 degree, so this is my 30 degree, or towards 210 degree. Okay, but this cannot be flipped because either the plane is dipping towards this direction or the plane is dipping towards this direction. Is it making sense to you, everyone? I hope it is. And then, of course, a line is defined with trend and plunge. A line is defined with trend and plunge. And we write down like 30 degree towards 120 degree. So that means the plunge is 30 degree and 120 degree is the trend. Okay, so if I just try to visualize how this plane will be, so this is north, east, south, this is west, right? So it has a plunge of 120 degree. So that means the projection of that line has an angle of 120 degree. So 120 degree means, so this is 90, 120 is somewhere here. So the projection is here. Okay, so the projection of that line is here. Okay, and then it has a plunge of 30°. So that means I have to go in the vertical plane. So this is my line OA, and this is 30°, and this is 120°. Understand my point? So this is my plunge, and this is my trend. Okay?
So in this case also the trend can be plus 180 degrees as well.
No, it cannot be. Why not?
Uh,
So let's try to do that. Okay. So 120°. Okay. So if I add this 180°, what does this mean? That the line is here, right? The line is here, right? Yeah, 120 plus 180 means 300. This is the line, right? Now, if I do a 30°, what would happen? The line will be here. You understand my point?
okay,
This
so
line
yeah,
and
got
this
it.
line is not the same line.
Yes, sir. Got it. Yeah.
Yeah. So here it cannot be interchanged. Okay. Here it cannot be interchanged. Only strike can be interchanged. Strike, I can add 180°. No problem. But dip direction cannot be changed. In case of a line, this is the first thing that is given is called plunge, and the second thing is the trend. In case of a plane, I first write the strike, then I write the dip, and then I write the dip direction like this. So strike, and then there is a like a stroke, oblique, dip. This is the normal convention. And then there is this arrow, and then I write down 120 plus 90 means 210. Either 210° or okay. So you have to have this. So this is very humble one plane and one line, okay, which can be situated anywhere in the horizontal in a 3D frame. Okay, and you have to be extremely familiarized with when I say, I give you a strike, dip, and dip direction. That particular plane should immediately come to your mind. If I give you a particular trend and plunge, that particular line should immediately come to your mind. Okay, it should not be. I mean, you must practice this so much that it becomes quite natural to you. Okay, whenever I say a particular attitude of a line or the attitude of a plane, it should very quickly come to your mind, right? And because these are the two very fundamental uh, building block of any geometry that we will build, right? Of course, we are not going to restrict ourselves with one plane and one line, right? We are going to go beyond that, and we are going to look into very, very, very complicated structures. So if these two things are not clear for you, they will be, I mean, you will be lost in no time. Okay. So it's important. It's nothing to mug. It's absolutely conceptual. You have to understand, draw, and get it into your mind. Okay. If I give you a particular data, what it means in 3D. Okay. Of course, then you should be able to plot them in stereographic projection, which will be the next step, which you have all done um, in your lab class for introduction to uh, earth and environmental science. But we will do it again. Of course, we will not be restricting ourselves just by plotting line and plane. We will do all sorts of operations. We will rotate, we will fold, we will fault, and things will be very, very complicated. I mean, it's not complicated because things will pile up, of course, right? So it's important that while we are in the very beginning, you get these definitions and things very, very clear in your mind. Okay, in your head space. That is very, very important. Okay, so let's proceed. Is there any question around dip and strike, dip, strike, trend, plunge, ladies and gentlemen? You can tell me now.
Most of the structures in around the Earth are three-dimensional. So, what is the use of defining a line and its projections? Like, I can understand the use of
No,
strike, dip, and
the line can be three-dimensional as well, right? All the lines that we have seen are three-dimensional.
yes, sir. But where in nature would you actually find a line?
Where two planes intersect.
Okay, okay, sir. Got it.
Yeah, whenever you will see there are plenty of linear elements that you have to map in your lifetime. Okay, so but you will find a lots of lines that you have to draw.
Okay.
So anywhere two planes intersect, you will find a line. For example, you talk about fold axis. You know what is fold axis? You will see what is fold axis in greater detail, of course. But where two fold limbs actually intersect, that is a fold axis.
Okay. Yeah,
And
got it.
you have
Thank
to
you, sir.
map that. Yeah. So that's why you need to learn about a line as well. Okay. Then, for example, I don't know, have you studied sedimentology already or not?
No, sir.
Sedimentology you have studied already
No, sir, we haven't.
in this semester. Na? You will learn
It's in
something called paleocurrent direction. Okay, from which direction one particular flow used to, I mean, say for example, one particular river used to flow, and that we will also calculate in our structural geology course. See from cross stratification. Okay, so that is where the cross stratified strata, I mean the four set, what we call them, the cross stratified beds actually intersect the horizontal plane. Okay, and that gives you a line, okay? And that lines define the direction of paleocurrent, the flow of the particular river that you are not seeing right now. Okay, just by looking at a rock, you can know whether that river, whether it flowed from north to south or east to west. Okay, and whether it changed its direction in its during its lifetime. Yeah, and there are so many places where you will be able to use the concept of line. Okay, it will. Okay, any other questions that you might have? Okay, if not, then let's proceed. So structural geology characterizes the deformation structures. Okay? This is a very important term to understand. Deformation structures. So the structures, the geometries that are geometry formed by deformation. Okay. So why I'm emphasizing on deformation? Simply because geometries will also form because of deposition, right? Say for example, a sedimentary bed that has a geometry, right? That has a geometry, but that has a geometry, right? But we are not going to be. I mean, that is our precursor geometry, but we will not be much interested in studying them in structural geology. That is our precursor geometry. Structural geology exclusively deals with the geometry which are formed due to deformation. Displacement, kinematics, we just talked about, and forces that produced the deformation. That is what we call the dynamics. Field-based, it's a field-based discipline. Structural geology operates at scales ranging from 100 microns to hundreds of meters, from grain to outcrop scale. Okay. So what are the tools that we are going to use? Of course, field study, rock deformation, analog experiments, and most importantly, numerical models. In my lab, we are mostly, we do a lot of field study and all, but we are we do expertise in analog experiments and numerical models. Okay, I will try to give you a glimpse how numerical models, especially finite element modeling and stuff, and analog modeling is done in case of structural geology. But that's not exactly purpose of this particular course. Our course is still to give you understanding about the basics of structural geology. But every now and then, I will give you references where uh, these advanced techniques will be highlighted. Now you can see here a beautiful field photograph. You can observe that this particular black layer. Okay. Before we do that, what do you see? Let me ask. One of you can unmute and tell me what do you exactly see in this particular picture. Suppose you were standing in front of this picture. What do you see? And your observations can be as lame and as basic as possible. No problem. Just tell me what do you see. Anyone?
Plane.
No, of course you do see plane, but you see layers, right? You see alternate black and white layers. Do you see that?
Yes, sir.
Alternate black and white layers, you do see that. Okay. Now you see that some of the layers are like here, if I see, these layers are a bit continuous, right? Yeah. But you can also observe that these layers, some layers are actually fragmented, right? You see, they are fragmented. So I see some continuous layer, although not continuous in the whole scale. But maybe if I take this scale, this is pretty continuous. But then we also see some in the same scale. We see some discontinuous layer. Okay? You see, whenever you take like a field photograph, you must have a scale. Okay? Because if I tell you that this represents the whole Alps, or this is a picture under the microscope, you will not be able to make out what it is. Because if I look at a photograph without a scale, a geological photograph is meaningless. Okay? A photograph must have a scale. From now onwards, whenever you take a photograph that is of your geological interest, and I am sure you will take a lot in your life, okay, because that's one of the primary tools that you use to study nature, okay, you must use a scale. For example, here, a pen is used as a scale. Now, you know that this particular length is as long as of a pen, okay. Now, I can imagine a pen is of, maybe 10 centimeters or so, right? So this is around 10 centimeters. I know. Yeah. Then I know what is essentially, if I now do a proportion, what is the scale of this particular photograph that I am looking at. Okay. So this is 10 centimeters. That means I am not looking under a microscope. Neither I am looking at something which is very big. So we are looking at something like, maybe 1 or 2 meter of an exposure. That is what we are looking at. Right? So a scale is a very, very important part of a field photograph. Okay? That is one lesson that you have to understand. And the second thing that you make certain observations. You see that there are alternate layers of white and dull bands, white and bright bands, okay? White and dark bands. Yeah. Some layers are continuous, some layers are fragmented, and you also see that these layers, some layers are like a little bit folded, wrinkled. That is the enough sort of observation that you can make in this particular case. Okay. Now you are restricting your observations in a scale which is like an outcrop scale. And when you do that in this sort of outcrop scales, maybe all the way up to maybe under microscope to hundreds of meters, that is the general scale of structural geology. Although when you scale it up, the same sort of observations, when you make it in a very large scale, okay, and that is when we call it, you do the same sort of observations, but at a very larger scale, we call it as tectonics. So tectonics picturizes the geological scenario, maps, cross sections, 3D presentations, etc., of deformation, together with the information from petrology, stratigraphy, geophysics. Tectonics operates at scales ranging between 100 meters to thousands of meters, okay, mostly confined on the movement of the plates and their mutual interactions. Okay, continental rifting, disinformation, subduction, collisional processes, mountain building processes, etc. Tools still same: field study, analog experiments, numerical modeling. So, what is the basic difference between structural geology and tectonics? Is the scale. So when you study it in an outcrop scale or in the microscope in a smaller scale, it is called structural geology. And when you put a lot of structural information together and you try to build up the story of a continent, maybe for India or maybe for Asia, maybe for Gondwana land, when you do that on a larger scale, we call it tectonics. Okay, I hope this particular definition is clear to you. Okay, so structural geology is mostly restricted in a. So structural, it's not restricted. Let me put it this way: that you have to study structural geology of different parts of the world to build up the tectonics of a larger continent. Okay, you study the structural geology of Bhopal, and then you build up the tectonics of India. Okay, I hope this is clear to you. And the final thing that I'm going to stop the lecture today with is something called geodynamics. And geodynamics discusses about the forces and the processes that drives the plate tectonics and deformation of materials inside the earth. Mantle convention, plumes, we talked about them before. The study of geodynamics operates at scales more than hundreds of kilometers. Here also we do analog experiments and numerical models, of course. So here we are looking more at the process. Tectonics and structural geology is more about the product. Geodynamics is more about the process. Okay, and it all depends on the scale that you are looking at. Okay, so fragments of structural knowledge builds up a geodynamic model or a tectonic model of a larger scale. Any question that you might have, and then we will stop it here. We will continue on Thursday. Any question? Anyone? Okay, if not, I will stop it here. What I recommend strongly, but between today and next Thursday, okay, you familiarize yourself with deep strike, deep direction, trend plunge. Okay, read SKG's book, get yourself familiarized with these concepts as much as possible, so that we can proceed with a more concrete understanding. So I'll stop it here, and I'll see you on Thursday. Thank you very much.